This is exercise 4.3 on the properties of logarithms. Anytime you study a particular process, type of function, then you usually look at properties that it has. So let's talk first about some general properties. I have these separated, and this comes from your textbook. These are the general properties. And then it shows them in application with common logs. Remember, common logs have a base of 10, and it shows these same properties with natural logarithms, and these are base e. And the first couple, if you thought of that as log base 10, which we don't write, of 1 equals 0, and this is true for any base, the reason being, what power do you raise 10 to get a value of 1? 10 to the 0 power is 1. Any base to the 0 power is 1. So that's where that property comes from. The next one, if you have a log base 10 of 10, it's equal to 1 because what power do you raise base 10 to get 10? 10 to the first power is 10. If you just talk in terms of generalities, base b, any base, to the first power, there's the exponent, is the base. This is true for base 10 or base e. Finally, the last ones are inverse properties. I think we've seen them in at least one other exercise. Log base 10 of 10 to the x is x. So in other words, if the base of the logarithm is the same as the base in the argument being raised to the x power, you get x. Number 4 works backwards. If you have base 10 to a log power, which is also base 10, you get x. Those might come in handy to simplify things as we move on. Now we're actually going to do exercises on two other sets of properties, one being expanding logarithms and one will be condensing logarithms. When you expand logarithms, if you have a log of an argument, remember that this is the argument, and the argument has an operation. If it has multiplication, division, or a power, then this can be expanded so that each argument is a single term or a single variable. All right, the first one says, if you have the log, any base, of a product, it is the log of the first factor plus sign, log of the second factor. That's called the product rule for exponents. If you have log any base of a quotient, it is expanded into the log of the numerator minus the log of the denominator. The last one is the power rule. If you have log base b of something to a power, that power becomes a factor. It will sometimes look like a coefficient in front of the log. So let's look at these. Expanding and condensing, I think you will find pretty easy if you just identify what the situation is. All right, it says use the properties of logarithms to expand the logarithmic expression as much as will evaluate without using a calculator. Well, I don't know, maybe we'll need to do that, maybe we won't. The first one, remember the base doesn't matter, but you do have to type it. So this is a product. It is a product of arguments. So it will be the log base 7 of the first factor. It becomes plus log base 7 of the second factor. I can't simplify those. I don't know what they are. Usually you could only simplify if one of these rules comes into play. So we'll kind of watch out for those. That's all there is to it. We have expanded it. This will be in your toolbar. You will put in the base. Make sure it matches this base. The next one, same instructions. This is also a product because I have argument 2 times x. So this will become the log base 2 of 2 plus sign the log base 2 of x. Now this looks like something I might need to think about. All right, let's look at this property. This is log, well, I won't circle that one, I'm sorry. Let's circle this one. If the base is the same as the argument, you get 1. The base is 2, the argument is 2. This simplifies to the number 1 plus log base 2 of x. We want to make sure that we check to see if one of those earliest properties is needed to simplify something. Okay, the next one, whoops, I'm so sorry. All right, the next one, we have a log. This is a quotient because there is division. So this is the log base 5, because that's a little base 5, of the numerator minus the log base 5 of the denominator. Can I simplify anything? Well, remember, if the base of the logarithm is the same as the argument, you get 1, because logarithms are equal to exponents. What exponent do you have to raise base 5 to get 5? The answer is 1. So this is 1 minus log base 5 of y. All right, let's look at number 4. This is using common logarithms. It is a quotient. Because I see division, so it is the log. It's a common log, so I don't write anything, of x, and it is division, so it's minus the log, common log, of 1 million. Whoops, that's a 0. Now this is base 10. We should be able to simplify this because this is a power of 10. I don't know if you would go through this step, but I don't know what the common log of x is. But this is the common log of 10 to the 6th power. Let's go back for a minute and look at those properties. In fact, we can even look at the common log properties, and it says if you have a log, common log, of 10 to a power, it is equal to the power. So it might be helpful to have those just sitting around, write them down. So that's 6. This is log base x minus a 6. So we're looking out for simplifying. All right, this is also a quotient. Working now with base 4. So this is log base 4 of 64 minus, because with a quotient you always subtract, log base 4 of y. Now log base 4 of 64. I don't know if you're going to recognize it, but 64 is 4 to the, what is it? 4 to the first is, I'll do it over here. 4 to the first is 4. 4 to the second is 16. 4 to the third is 64. So 64 is 4 to the third. So this is the log base 4 of 4 to the third power minus log base 4 of y. When your base is the same as the base here, you get the exponent. So that's 3 minus log base 4 of y. That may be a little challenging if you are not aware of things like this. Number 7. All right, don't think I'm going to be able to simplify this. But it is a power. When you see your argument with a power, you're using the power rule. Take that power and it becomes the coefficient. So it is 4 log, well, I'm not writing correctly, base d of x. And there's nothing I can do with that. All right, the next one, this is also the power rule. I see an exponent there. So this will be negative 4 log m, because the exponent becomes the coefficient. And that's all there is to it. The next one, this is the ln, whoops, oh, I'm so sorry. All right, this is the ln of the 11th root of x. So let's go over here and remember something. The 11th root of x. Roots can be written as fractional exponents. Whoops. This is x to the 1/11th power. So this is natural log of x to the 1/11 power. So it is the power rule. You're going to have to remember that radicals, square roots, cube roots, and so on, can be written as fractional exponents. Now it's the power rule. This becomes the coefficient, so it is 1/11 times the natural log of x. All right, I think we will now be combining several of the rules together. Just look at the argument. I see several things. I see a power on the x, and I see a product. All right, so this will equal the log base b, take care of the product first, of x to the 7th plus sign log base b of y. Now, power rule. This will be 7 log base b of x plus log base b of y. Some people ask, well, how do I know when I've finished? How do I know when I've done enough? The arguments of the logarithms will be single characters. And then remember, a product turns into the sum of the logs, and a power turns into a coefficient. These may be tedious to type in. Number 11. I see a fraction, which is a quotient. I see some powers, and I see a product. Powers are taken care of last in the expanding. So this is log base b. This is how I do it, and I think this is kind of a shortcut. Every factor in the numerator gets added. Every factor in the denominator gets subtracted. So this is log base b of x to the 3rd plus log base b of y. Those are both positive because they're factors in the top, minus, there's the quotient, log base b of z to the 4th. It's not finished because this is not just x, this is not just z. So I will use the power rule That gives me 3 log base b of x plus log base b of y minus 4 log base b of z. Just an x, just a y, just a z. I'm done. Next one. When you see a square root or any other root, change it to a fractional exponent. So I'm going to remind you that the square root of a is a to the 1/2. So this is log base d of a to the 1/2 b to the 4th over c to the 2nd. When I expand it, each factor of the top is a plus, each factor of the bottom is the subtract. So this is log base d of a to the 1/2 plus log base d of b to the 4th, get rid of this, minus log base d of c to the 2nd, minus because it was on the bottom, so it was the quotient. Now exponents become coefficients. This is 1/2 log base d of a plus 4 log base d of b minus 2 log base d of c. I'm done. My arguments are just a, b, and c. So it has been expanded. This is called condensed form, one argument. This is called expanded form, many different terms, each argument a single character. All right, now we're going to go in reverse. We're going to condense the logarithms. To condense a logarithmic expression, we write the sum or difference of 2 or more logarithms as a single logarithm. And these are the properties. If you have a sum, it turns into a single log with the product of the arguments. If you have a difference, it turns into a single log with a quotient. If you have a constant times a log, well, it doesn't even have to be a constant, it could be anything times the log, it becomes the exponent of the argument. All right, here, this is a sum, which means it will turn into the product. This will be the common log of 20 times 5. Multiply the arguments. Well, that is the log of 100. And then I think about that. What's my base? This is a common logarithm, so the base is 10. And is 100 a power of 10? Yes. This is the common log of 10 to the 2nd, which is 2. Now, right here is where I condense them. Everything else was simplifying, but you must simplify these to get credit. All right, number 14. It's also a sum. That means that I will condense it to a single logarithm. The argument will be 18 times x. The reason I put the 18 in front, it's just a little more common than saying x times 18. I cannot do anything to simplify, so that's my answer. All right, a minus. This is a difference. A difference turns into the quotient of the arguments. So this is the common log, because I see no base written, of on top is 5x plus 3, and on bottom is x. If it could be reduced, we would, but no, you cannot divide that x out with that one because x is not a factor of the whole numerator. So we're finished there. Number 16, this appears to have two things. I see a sum, but I also see this coefficient 8, which is going to be a power. We're going to take care of the power first. when we expand, we take care of the power last, but when we condense, we take care of it first. So this will be the log of y plus this 8 is going to retake its role as an exponent, log of z to the 8th power. Now I see it as a sum, so I can condense further. This is a single logarithm. It's a common log. Because it's plus, I will write this as y z to the 8th. And it's pretty common to put that in parentheses. So we had two steps. The coefficient of 8 became the power. Then I saw it was the sum of two logs. They had the same base, so I could condense them to a single log. Oops, let's look at 17. All right, minute you see coefficients, I hope you will attack those first. This is going to become the 2 gets to be an exponent, 5 gets to be an exponent, so this will be log base b of x to the second. It's still plus log base b of z to the 5th. So my first step just pulled those coefficients into their roles as exponents. Now it is the sum of these two logarithms. They do, by the way, have to have the same base. We're going to have log base b of, when it's a sum, turns into a product, x squared times z to the 5th. All right, next one. Remember, always, powers first when you're condensing. Those coefficients become powers. This will be the natural log of x to the 5th plus the natural log of y to the 2nd minus the natural log of z to the 3rd. Now, sums, product, minus quotient. This will become a single logarithm. That's your goal when you're condensing. What will go as the argument? You'll have an x to the 5th, y to the 2nd on top because they're products. They're positive, so they become part of the product. Because this one is minus, it is a z to the 3rd. If I had another minus, it would go down here with this one. All right, that is expanding and condensing. There really are only three rules. We have the product turns into a sum, the quotient turns into a difference, and the power turns into a coefficient, or vice versa. Now, we are using calculators that only have two different log keys. We have this log key, which is a common log, base 10, and we have this log key, which is a natural log, which is base e. What if I need to use a different base? All right, there is a formula called the change of base formula. If you have a logarithm, base b of some argument, and you don't know anything about base b, maybe it's 7, maybe it's 9, maybe it's pi, but it's not 10 and it's not e, then you can change it using either base 10 or base e into something you can work with. So you can say it is the log of a new base of m over a log new base of the old base. Now that sounds a little confusing when I said it, but let's look here. If you have log base b of m, if you want to, and it does not matter, if you want to use common logarithms, it is a common log of m over the common log of the old base b. If you want to use natural logarithms, it is the natural log of m over the natural log of old base b. Because it's a ratio, you get the same answer, no matter how you do it. All right, this one Number 19 says use common logarithms or natural logarithms and a calculator to evaluate the expression. Now you have a choice of two different answers that you could put right here. You could use common logarithms because it says to use either one. The answer here could be log, which is a common logarithm, of 16 divided by the common log of 18. That is one way the answer could be written. Or it could be the natural log of 16 over the natural log of 18. Either answer is okay. No matter which one you do, it wants you to then actually put it in the calculator, and it says do not round until the final answer, 4 decimal places. Okay, I'm going to do it both ways. I did not intend to close my calculator, and I did. There it is. I'm going to move it over here. Well, I was going to move it over there. There it is. All right, if I do it this way, I have the log of 16, close parentheses, divided by the log of 18, close the parentheses. All right, and we will get, we want to round this to 4 decimal places. This is 0.9592 and it stays a 2. All right, or what if you had chosen to use natural logarithms? It would be the natural log of 16, close parentheses, divided by the natural log of 18, close, because remember the denominator is the old base that you didn't want to work with. Enter. Hopefully you see you got the same answer. Okay, there it is. Oops. Well, my goodness. All right, I'm just going to delete that, and let me see if I can grab it and do better with it. There we go. So you can see that you could do it either way. Let's look at number 20. It does not ask you to type in what process you used. So on your calculator, you will either do the common log of 15 divided by the common log of the old base, 19, or you'll do the natural log of 15 divided by the natural log of 19. So clear this. I'm just going to do ln 15 close divided by ln 19. Remember, ln is just a logarithm base e. Does not matter, but we got, let's see if I can move this over. Oh, things. Oh, I'm going to pause and fix this. All right, I got things back in order. So now let's look at the next one. We're just going to do this several times. On this one, suppose log base 13. I have no idea about log base 13. So I will take the log of 89.5 and I will divide it by the log of 13. And that's how I will get a value. So common log 89.5 close parentheses divided by common log 13 close. and I have 1.7522. All right, I'm going to fix that. All right, even though I haven't been writing those answers, I'm leaving them on the screen right here. But please remember, maybe I should write it, this answer will be 1.752, and the 1 behind that, the 7 behind it, rounds it to a 2. So on these, it's telling you to round to 4 decimal places. Whoops, sorry. And it will count it wrong if you don't. All right, the final one of these, let's suppose I do the natural log of 25.8 divided by the natural log of 0.9. I have no idea what that is, so I go to the calculator and natural log 25.8 close divided by natural log 0.9. There is no particular reason that I've done some of these with natural logs and some with common logs. I just want you to see you could use any base of a logarithm. So I get negative 30.85, and I will keep it 0, 0. All right, so I've put this little screenshot right here and typed the answer rounded to 4 decimal places. Now, you can use this change of base to actually graph functions that are not base 10 or base E. So that's very, very helpful. What you will do is if you have y equals log base 6 of x, you know generally what it looks like because you know what log functions look like when their bases are greater than 1. But if you wanted an exact graph on your grapher, you could not get base 6. So you would say, well, I'm going to use common logarithms. So it is the common log of x, and that would be in parentheses on the grapher, divided by the common log of 6. You would type all of this in and then look at the graph. So let's do that. Let's go to the y equals. And type in the common log of variable x, close parentheses, divided by the common log of just the old base 6. And let's see, they are using a rather small window. They're going for the x's, they describe it right here. 0 to 10, scaled 1, negative 3 to 3. So let me mimic that window, and they are doing 0 to 10 and negative 3 to 3. Because I scaled this exactly like they scaled it, I don't have any trouble deciding which one it is. Let me pull it down here. I'm going to shrink it just a little bit. All right, which one does it look most like? The shape, it's definitely not this and it's not this. The shapes are the same on these two, but this is not rising very quickly, and so here's my 1, 2, and 3's up there. It looks just like that one. It does not look like that one, so my choice is D. So I recommend that you set your window there so that you can do it. And by the way, here you would put in it's not in the y equals, but they're just having you practice log of x divided by log of 6. And it should be okay if you chose to use natural logarithms. Let's look at 24. On this one, we don't have to do that first step. We're just going to go to the grapher and say, okay, y equals, I'm going to use natural logs this time. It does not matter. I'm rewriting this using the change base formula. It's the natural log of x, that'll be in parentheses, divided by the natural log of 2. So let's pull up the grapher and go to y equals, and I can clear this out. This is, I chose natural log, no particular reason. Natural log variable x, close, divided by natural log of 2, close. I'm going to look at these windows, okay, because I want my graph to match. 0 to 10 in the x's, got it. But the y's are a little different. So for the y's, it's negative 5 to 5. All right, look at the graph. It is important that you have the same window. By seeing that it's the same window, if I grab this and perhaps shrink it just a little bit and then put it right here, you can see that those are the same, and so my choice is D. All right, number 25. You can even do it when the argument is more complicated. All you have to do is remember that log base 6 of anything is, I'm going to use common logs, the log of x plus 1 divided by the log of the old base you don't want, which was 6. That's all you have to do. So let's go to the grapher, y equals, clear that out. So this is the common log of x plus 1, close, divided by the common log of 6, close. And window, let's take a look at the window. They are using negative 1 to 10, so I'll put a negative 1 in there. 10's okay. Go on down, y's, negative 4 to 4. Matching the window, graph. Okay, and there's something else I want to discuss about this. Put it right there, a little bit smaller. It does match with this one, and I hope maybe you anticipated some of this. In the argument, there is a plus 1, and that should have told you it would look like a log graph, which normally cuts through at 1, and it will cut through at 0, and it did. All right, I think that's it. And now use the properties, keep them written so that you can use them as you need them.